Look at these solid, blank wooden blocks dropping sequentially onto this glass track. This is how a computer actually builds text. A string is a physical, contiguous array of character bytes laid out side by side in system memory. To read a word, the computer's processor must scan these bytes one by one, moving in a strict linear sequence from the first memory address to the next. There is a severe mechanical vulnerability in this design. A processor reading these continuous blocks possesses no inherent concept of where a word ends. Left to its own devices, the read operation will march straight past the intended text and begin parsing garbage data from adjacent memory sectors infinitely. This animated diagram demonstrates the required fix used in foundational languages like C and C++. Notice the distinct, brightly colored block dropping in immediately after the final character. This is the null terminator, represented by a backslash and a 0. It acts as an absolute stop sign. As the scanning pointer sweeps across the characters, it encounters the null terminator and immediately halts the memory read operation, securing the system from reading out of bounds. Modern high-level languages automatically append and hide this terminator behind the scenes. However, the underlying mechanical boundary rule still governs how the physical hardware processes memory. Text is a rigid array, strictly governed by hard physical termination rules in the hardware. Before a single character can be stored, a program must perform an active declaration. This is the process of requesting a highly specific block of physical memory space and assigning an identifier to it. This physical label attached to a cardboard storage box illustrates how C and C++ handle declaration. You declare strings as raw character arrays or pointers, demanding strict manual oversight. You must explicitly tell the system exactly how large the box needs to be. Object-oriented languages like Java and C# take a different approach. They wrap strings in built-in classes, which are sophisticated structures that calculate and manage the exact memory sizing automatically upon declaration. Python and JavaScript simplify the architecture. In these environments, there is no single character data type. A single letter is declared and treated entirely as a string of length 1. These high-level languages utilize varying syntax, single quotes, double quotes, or backticks, to give developers flexibility in how they command the system to allocate this memory. The syntax you select directly dictates how the computer architects and secures that specific block of text in its physical memory. Once memory is claimed, it is bound by a critical distinction, the difference between mutability and immutability. Look at the whiteboard on the left side of this split screen. This represents a mutable string, the default architecture in C++. Mutable structures allow their internal bytes to be rewritten directly in place, just like erasing and replacing a single letter on a board. In-place updating requires exceptionally low CPU effort. Because the physical memory address never changes, the system can edit text without requesting new space. Immutable strings, enforced strictly by Java, Python, and JavaScript, operate under opposite rules. Once a sequence is created, that specific memory block is permanently locked. The values inside can never be altered. Watch this dictionary page crumpling up and instantly being replaced by a pristine new sheet. This is the mechanical cost of editing an immutable string. To change even a single character, the system must allocate entirely new memory space, print the new modified word there, and abandon the original. This generates waste. The system must frequently deploy a garbage collection process to locate and destroy the abandoned memory blocks left behind by every immutable operation. This creates severe hidden performance costs. Executing high-frequency text edits in Python or Java triggers heavy memory reallocation and constant garbage collection, lagging far behind the raw speed of C++. The choice of programming language restricts the physics of text manipulation, forcing developers to balance the speed of in-place editing against the strict safety guarantees of locked memory. Translating standard text editing into these memory blocks reveals the physical labor required by the processor, starting with read-only sweeps. Calculating the total length of a string or searching for a specific character relies on the exact same mechanism, a pointer sweeping linearly across the array indexes, verifying the content byte by byte until it hits the terminator. Extracting a substring involves no immediate creation. The system simply identifies a smaller, continuous clamp of memory within the rigid boundaries of the parent string and returns those specific coordinates. Modification introduces a mechanical dilemma. Inserting a new character into a contiguous block of memory is difficult because there is no physical empty space between the existing bytes. Observe the array shifting process. To insert a character, subsequent bytes to the right physically translate one index right, opening a vacuum for the new character. Deletion requires the inverse. A target byte is destroyed, and right-side elements slide left to seal the space. If you execute these insertions or deletions in Java or Python, the processor endures the immutability penalty. It must execute these shifts while building a completely new array from scratch in fresh memory. Fluid text editing is a visual illusion. Inserting or deleting text relies entirely on mathematical array shifting operations designed to maintain a contiguous chain of memory. String concatenation expands on this architecture. It is the physical interlocking of two distinct memory allocations, reading the bytes of the second string and appending them immediately after the first to forge a continuous sequence. Advanced string manipulation demands complex algorithms. Consider the challenge of reversing a string. Doing this naively requires duplicating the entire word backward into a massive new block of memory, which wastes system resources. This animated array introduces a standard solution for in-place data manipulation, the two-pointer technique. Notice the two distinct indicators appearing beneath the memory blocks, one placed at the extreme left start and one at the extreme right end. The algorithm commands the two extreme pointers to swap their corresponding physical bytes directly. Then both pointers step exactly one index inward toward the center of the array and command the next set of bytes to swap. This mechanical cycle repeats rapidly. The pointers march inward, swapping bytes until their paths cross in the exact center of the string, signaling that the reversal is complete. This technique achieves an O of 1 space complexity. It requires absolutely zero extra memory allocation because it leverages the existing physical architecture of the string. Algorithmic efficiency in text processing is achieved by intelligently manipulating these reference pointers rather than aggressively moving bulk memory. String rotation pushes pointer manipulation further. It shifts characters directionally to the left or right, but requires any byte displaced past the array boundary to immediately wrap around to the other side. This requires strict boundary logic using modulo arithmetic. When a character falls off the terminal index, the math dynamically calculates the correct remainder, teleporting that exact byte back to the starting index to maintain the sequence. These mechanical checks scale up to address a common application of string logic, identifying a palindrome. Watch this glass mirror dropping perfectly into the center of these wooden blocks. Mathematically, a palindrome is a string exhibiting perfect structural symmetry. Developers reuse the two-pointer technique here, placing pointers at both ends and marching them inward. Instead of swapping, the algorithm validates the palindrome by checking if the converging memory addresses hold mathematically identical values. If even a single pointer comparison fails, the symmetry is broken. The algorithm terminates the sweep immediately, definitively proving the string is not a palindrome. These operations demonstrate that string manipulation is achieved through the mechanical shifting, mirroring, and bounding of contiguous memory blocks. Mastering this physical architecture provides the technical foundation for understanding complex data structures.